In this video, we're going to talk about the last section of chapter 6, which is working with Taylor series. So we're going to see how Taylor series is useful to find other series for other functions, and we'll be able to integrate some integrals that are very difficult to integrate using basic techniques that we've already learned. So let's start by talking about the binomial series. So the binomial series is actually the Maclaurin series for a function of this form. So if I have a function f that looks like 1 plus x raised to a certain exponent r, we can find the binomial series or the Maclaurin series for it using this formula of the summation. So this here is called the combination. It's a way to choose n elements out of r. So here we read it as r choose n, and it looks like r factorial over n factorial multiplied by r minus n factorial. So it's just like a value for a certain number. So don't worry too much about it. So now if we look at the expanded form for this series, it's going to be 1 plus r times x, r times r minus 1 over 2 factorial using this formula here, times x squared and up to n up to infinity. So it's just a formula that you should know. That's it. So it's not too difficult. It's just like a way to find the Maclaurin series for a function of this form. We use the binomial series to find the Maclaurin series for it. And here, if you have like a different value for x, you just substitute it inside of here. So if that was like 4x, that would be 4x all to the n, and all of these would be like 4x squared and so on. Okay, so let's look at this example and see how we'll find the binomial series for a function of the form that we've talked about here. So here, my function f of x is equal to 1 plus x raised to the half. So here my r is 1/2. So if we want to apply the formula to get a series for this is going to be 1 plus 1/2 x plus half 1/2 minus 1, 2 factorial x squared plus up to 1/2 minus 1, and then 1/2 minus n plus 1 over n factorial x to the n up to infinity. So now let's simplify. This is gonna be equal to 1 plus 1/2 x. So now 1/2 minus 1, that's negative. So that's negative over 2 factorial multiplied by what? By 2 to the 2 squared, because 1/2 times 1/2. And we go up to infinity. Once you do that, you're going to get this form. Once you simplify, this is going to be 1 times 3 times 5 up to 2n minus 3 over 2 to the n x to the n plus 1. So these are all of the numerators once you subtract from here. Okay, so if you can see here, now we can have a general formula, which is 1. Now all of these terms, I can write them as a infinite sum when n equals 1 up to infinity. So that's negative 1 n plus 1 over n factorial. Then we have 1 times 3 up to 2n minus 3 over 2 to the n x to the n. So we were able to go from a function that looks like this into a series, which is the binomial series, and it's also the Maclaurin series. So don't worry too much about it, just like know the general form, be comfortable with like substituting and finding the general formula for the binomial series. Now we're going to see how we're going to use common expressed functions with Taylor series to find the series for other functions related to them. So this table you should be familiar with. For example, this function 1 over 1 minus x, this is a geometric series that we already know that has this form. And also e to the x, in previous videos, we were able to prove that this is equal to this. Similarly for sine, cosine, ln, and so on, if you apply the Taylor series formula, find the nth derivative and so on, you'll be able to see that these are the Maclaurin series for them. So now we're going to use these basic Maclaurin series for these general functions to find the Maclaurin series for other functions related to them. So for example, we want to find the Maclaurin series for sine x squared and e to the square x. Now here, we already know that sine of x is equal to this Maclaurin series from the table. So to find sine x squared, the only thing that I have to do is I want to substitute x squared instead of my x here. So if you do that, you're going to get negative 1 to the n, x squared, all to 2n plus 1, and you divide by 2n plus 1 factorial from 0 to infinity. So once you simplify, here I can multiply the exponents. So I'm going to get negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial from 0 to infinity. Similarly, for the second example, we already know that e to the x has this Maclaurin series from the table. So to find e to the square root of x, you just plug in square root of x instead of your x in the original Maclaurin series. So the square root of x is x to the 1/2 all to the n divided by n factorial from 0 to infinity. Now again, we're going to multiply the exponents. We're going to get x to the n over 2 over n factorial from 0 to infinity. So these are just tools that we're going to use to find Maclaurin series for more complicated functions that can be related to one of these functions. Okay, now let's try to find the binomial series for this function. Okay, so we're going to use the binomial series for the square root of 1 plus x and kind of relate it to this function here to be able to find the binomial series for it. Now, if you find the derivative for the square root of 1 plus x, you already know that it's 1 over 2 times the square root of 1 plus x. So the binomial series would be given as since this is equal to 2 times the derivative of this, the binomial series of this function that we want to find would be equal to 2 times the derivative of the binomial series for the square root of 1 plus x. But we already found it in the previous example. And once you take the expanded form of it, I just find the derivative for each term separately. And once we're done with finding the derivative for each term, if we write it as a general formula, that would be the series, the binomial series for the function that we want to find the derivative for. So let's find the derivative. The 1 would be 0. This is 1/2 minus. Now, since I have a 2 that I'm going to take down, 2 with the 2 factorial, that's 1 factorial. 2 squared x plus, similarly, the 3 goes down, so I'm going to have 1 over 2 factorial, 1 times 3 over 2 to the 3x squared, and so on until we get to the negative to the nth term. Now, similarly here, since I'm taking the derivative, I'm going to take the n down, and it would cancel with one of the n's here. So I'm going to have n minus 1 factorial, 1 times 3 times 5, up to 2n minus 3 over 2 to the n xn minus 1 up to infinity. Now, if you want to find the general form, once you distribute the two, this is going to be 1 plus the summation of, now since we want to find the sum starting at 1, this is going to be the sum of n over n factorial, because I'm taking the next term here. 1 times 3 times 5 up to 2n minus 1 over 2 to the n, because once you multiply the n, the 2 here, it would be back to n times x to the n. So here we were able to find the binomial series for this function using the fact that it's the derivative of, it's the derivative of this function, and you already know the binomial series of it. So here it's like, if you already know a series and you know that this series is the derivative of the other series, you just derive each term separately, then find the new formula of the series, and that would be the series for the function needed. And the last thing that we're going to talk about today is evaluating non-elementary integrals. So if we have an integral with an antiderivative that can't be written as an elementary function, so here this integral is called a non-elementary integral because we can't just find it using basic integration techniques that we've already talked about. So here, to evaluate this integral, we're gonna express the integrand, which is what's inside of my integral, as a power series, and then I'm gonna integrate each term separately and then create a formula. So the most famous example for this kind of integral is the integral of e to the negative x squared. You can try it, try different techniques, try different methods that we've talked about. You won't be able to integrate it. So here we're gonna go into the power series because I already know how to express e to the negative x squared as a power series. Once you expand that power series, you'll be able to integrate each term separately and then create a general formula. So let's see. Using the series from the table, I know that this is going to be equal to negative x squared to the n over n factorial from 0 to infinity. If you simplify, this is negative 1 to the n x and x2 to the n over n factorial, n equals 0 to infinity. If you expand it, you're going to get 1 minus x squared plus x to the 4th 2 factorial minus x to the 6th 3 factorial until the nth term, and you go up to infinity. Now if you take this integral with the expanded form of your power series here, we can easily evaluate it because I can easily distribute my integral over the sum and addition here, and I can integrate each term separately. So if you integrate, you're going to get c plus x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7 over 7 times 3 factorial, and then you can do it for the nth term, and so on. So we went from something that's very difficult to integrate into something that I was able to integrate in one line. So that's why power series are quite useful when we want to integrate something that's quite difficult to deal with. Similarly here, if I have cosine radical x, no matter what method you want to try, you won't be able to integrate it. So what we do is, I know that the power series of cosine is negative 1 to the n, x 2n over n 2n factorial. And if we plug in the square root here, we're going to get x to the 1/2 all to 2n factorial from 0 to infinity. If we simplify and then expand, you'll have this expanded form, 1 minus x over 2 factorial, 2 squared over factorial, minus, and so on up to infinity. Now, if we want to find the integral of this, you just take the expanded form of the power series, and just integrate each term separately. So here, let's integrate it. C plus x minus x squared over 2 times 2 factorial plus x cubed over 3 . And then you can do it for the nth term. And that would be your integral. And obviously you can just like write it as a sum and simplify it more. So yeah, this is how you use power series to integrate something that's not easy to integrate using normal methods that we've learned. So that would be it for chapter 6. If you have any questions, please let me know. And these are some practice problems that you can work on. And best of luck.